Today we'll be designing doubly reinforced beam. So what it means when we provide doubly reinforced beam while designing, we'll get to know why it is designed as doubly reinforced beam. The problem is design a RC beam supported on two walls 500 mm thick, spaced at a clear distance of 6 meter. The beam carries a superimposed load of 30 kN per meter. Use M20 grade concrete and Fe415 steel. So what they have given? They have given clear span, that is 6 meter, and they have also given wall thickness. Wall thickness is 500 mm. So superimposed load of 30 kN per meter. So 30 kN per meter and M20 grade of concrete and Fe415, that is nothing but our FCK is equal to 20 Newton per mm square and Fy is equal to 415 Newton per mm square. This is the data they have given. So we'll see how to design this. So step 1 is to find out the effective depth and width of the beam. So to find out the effective depth, as per clause 23.2.1a, page number 37, we'll see. So this is a page number 37 and clause 23.2.1. The vertical deflection limits may generally be assumed to be satisfied provided that the span to depth ratio are not greater than the values obtained as below. Basic values of span to effective depth ratios for spans up to 10 meter. For cantilever beam, they have given 7. For simply supported beam, they have given 20. So now we are designing the simply supported beam. So what they have said, for simply supported beam, our L by D ratio should not be greater than 20. So we'll take this. So I am taking L by D ratio as 14 and I rearranged it. We need to calculate the effective depth. So I moved D to here, rearranged it, that is L divided by 14. Our given L value is 6 meter. 6 meter is nothing but 6000 mm divided by 14. Simplify this, we'll get 428.57 mm. So I am making it approximate value, that is 450 mm. So effective depth is equal to 450 mm. After that, next step is to assume the effective cover. I am assuming it as 50 mm. I have taken 50 mm. So now we can find out the overall depth. Overall depth, capital is equal to effective depth plus effective cover. Our effective depth is 450 plus 50. After this, we will get D is equal to 500 mm. So this is the, we calculate the overall depth. After this, we'll go for calculation of width of the beam, that is B. We have the formula B is equal to 1/3 of effective depth to 2/3 of effective depth. I am taking 2 by 3 into effective depth. Substitute all the values. Simplify this. We will get 300 mm. So after the calculation of width of the beam, the next step is to calculation of the factored load. Factored load or ultimate load. The step 2 is to find out the factored load. So we'll go for calculation of self weight of beam. For that we have the formula B into D into rho. Rho is nothing but density of RCC, that is 25 kilonewton per meter. Substitute all the values. Simplify this. We'll get 3.75 kilonewton per meter. So after this, so our given load is 30 kilonewton per meter. So add both self weight of the beam plus given load. to get the total load. So W is equal to self weight of the beam plus given load. Substitute all the values, simplify this, we'll get our total load as 33.75 kilonewton per meter. After this, we'll go for the calculation of factored load. For that, we have the formula. Factored load is also called as ultimate load, that is denoted as W. For that, we have the formula 1.5 into our total load. So substitute all the value, 1.5 into our total load which we have calculated now, 33.75. So after simplifying, we'll get our factored load is equal to 50.62 kilonewton per meter. This is the process of calculation of ultimate load. So after the calculation of ultimate load, we'll go for the calculation of effective span. So step 3 is to find out the effective span, that is denoted as capital L. For that, as per clause 22.2a, page number 34, we'll see what it says. So this is page number 34, effective span. Unless otherwise specified, the effective span of a member shall be as follows. For simply supported beam or slab, the effective span of a member that is not built integrally with its support shall be taken as clear span plus the effective depth of slab or beam. So now we are calculating the beam. Now I will take beam or center to center of supports, whichever is less. So what they have said, to calculation of effective span, the formula is 2. They have given two cases. One is clear span plus effective depth, and second is clear span plus center to center of supports or supportive width. Which the first criteria is L is equal to clear span plus center to center of supports, or center to center of support is nothing but our support width. So our L is 6000 mm plus the support width which they have given is 500 mm. So substitute all the value, simplify this, we'll get 6500 mm. So second criteria is L is equal to clear span plus effective depth. So substitute all the value, simplify this, we'll get our answer as 6450 mm. So they have said our effective span value should be least of these two. So our L value should be least of these two. They have mentioned, clearly mentioned in clause 22.2a. So which is less? 6450 mm is less. So I am taking effective span is equal to 6450 mm. It is least. I am taking it. This is how we calculate the effective span. After this, we'll go for calculation of bending moment. So step 4 is to find out the bending moment. For simply supported beam, we have the formula mu is equal to W L square divided by 8. So W is ultimate load which we have calculated. So substitute all the value. So simplify this, we'll get our bending moment value is equal to 263.23 kilonewton meter. In terms of Newton mm, 263.23 into 10 to the power of 6 Newton mm. In terms of Newton mm. So next step is to find out the mu limit. So mu limit is equal to 0.138 FCK BD square. Substitute all the values. Simplify this, we'll get our mu limit value is equal to 167.67 kilonewton meter. Or in terms of Newton mm, 167.67 into 10 to the power of 6 Newton mm. This is how we calculate the mu limit and mu. So after the calculation of mu and mu limit, so our mu value is 263.23 kilonewton meter, and our mu limit value is 167.67 kilonewton meter. So it clearly says our mu is greater than mu limit. So when mu is greater than mu limit, the section is over reinforced. So NC, we need to design the doubly reinforced beam because our mu value is greater than mu limit. So when the mu is less than, so when mu value is less than mu limit, we need to go for the singly reinforced beam design. So here our mu value is greater than mu limit, so that we need to design the doubly reinforced beam. This is how we calculate the mu and mu limit. After this, we'll go for the step 5 is to calculation of the area of compression reinforcement and area of tension reinforcement. So the main difference between singly reinforced beam and doubly reinforced beam is, in singly reinforced beam we have to design the only tension reinforcement, but in case of doubly reinforced beam we have to design both compression reinforcement as well as tension reinforcement. So I will show how to design compression reinforcement and tension reinforcement, and this is the core difference between the singly reinforced beam and doubly reinforced beam. So we'll see one by one. So first we'll go for the calculation of compression reinforcement, that is denoted as ASC. For that, as per G1.2 page number 96, what it says we'll see. So this is the page number 96, G1.2 section with compression reinforcement, where the ultimate moment of resistance of section exceeds the limiting value mu limit. Compression reinforce may be obtained from the following equation. What they have said, whenever mu value is greater than mu limit value, we need to provide the compression reinforcement in the form of, by using following equation, that is mu minus mu limit is equal to FAC into AC into D minus D dash. By using this formula, we will calculate the AC. So we'll see. So I have written same formula which is given on page number 96. So by using this formula, we'll design the compression reinforcement. So I have rearranged this. So AC is equal to mu minus mu limit divided by FAC into D minus D dash. Call it as equation number 1. So to find out the AC, now we need to find FAC by using SP16 page number 13 and table number F. I will show how to design it. So before going to our SP16, now we'll calculate the D dash by D. So our effective cover value which we have taken is 50 mm and our D provided is 450 mm. Simplify this, we'll get 0.11 has our D dash by D value. So now to find out the FS value by using table F and SP16. So this is the page number 13 of SP16. So by using D dash by D value, we will calculate our FSC value. So our D dash by D value is, which we have got, is 0.11. So 0.11 means that value is not where it comes. It comes in between 0.10 and 0.15. It comes in between these two. So for 0.10, the corresponding our 415 value is 353, and for 0.15 is 342. By using this value, we'll calculate our FS value by interpolation method. The I will write down this value. I will show how to do the interpolation by using this value. So for 0.10 we have the corresponding value 353, and for 0.15 we have the value Fi value 342. Now we need to calculate the what is the value for 0.11 by interpolation. We'll see. So our Fs is equal to 3.53 minus y minus means this value is goes on decreasing, so I'm taking minus, and greater value minus least value. Greater value 353 minus 342 divided by greater value minus least value 0.15 minus 0.10 and into the value which we want to find out, that is 0.11 minus the least value 0.10 by so calculate this, we'll get our Fs value is equal to 350.8 Newton for mm square. After the interpolation we'll get our Fs value is equal to 350.8 Newton per mm square. This is how we calculate the FSC value by using SV16. So now after this, substitute the Fs value in equation number 1, that is As is equal to mu minus mu limit divided by FSC d minus d dash. Substitute all the value. Simplify. After simplifying, we'll get our AC, area of compression reinforcement, is equal to 681.01 mm square. This is our AC value. So this is how we calculate the AC value. So now next step is to assume 20 mm pi bars to calculate the number of bars required to carry this area of compression reinforcement. So for that, let us assume 20 mm pi bars. So we'll find out the area of each bar, that is A is equal to pi by 4 into d square. I have taken diameter is equal to 20, so 20 square. After simplifying, we'll get 314.15 mm square. This is the area of each bar. Now we'll calculate the number of bars. For this, AC divided by small AC. So area of compression reinforcement, which we have calculated just now, that is 681.01 divided by our area of each bar is 314.15. So simplify this, we'll get 2.16. So we cannot provide 2.16, so I'm taking it three numbers of bars. So now we need to calculate the AC provided. For that, we have the formula number of bars into area of each bar. So substitute all the value, simplify this, we'll get 942.45 mm square is the area of compression reinforcement. This is the AC provided. So provide three numbers of 20 mm pi bars at compression reinforcement. So this is how we calculate the AC provided. So after that, next step is to find out the area of tension reinforcement. I will show. So next step is to find out the area of tension reinforcement. So for that, as per G1.2 page number 96, what it says we'll see. So this is the page number 96. The total area of tension reinforcement shall be obtained from the following equation. So we need to calculate the area of tension reinforcement by using this equation. AST is equal to AST1 plus AST2. So AST1 is area of the total tension reinforcement, and AST is the area of the total tension reinforcement. AST1 is equal to area of the tensile reinforcement for a singly reinforced section for mu limit, and AST2 is equal to AC into FAC divided by 0.87 Fy. By using this formula, we'll calculate the AST2. And by using this, we'll calculate the AST1. So we'll see step by step. So AST is equal to AST1 plus AST2. This is given. This formula is given and page number 96. By using this formula, we'll calculate the AST. For AST1, what we have to do is, there is one formula given on page number 96, G, that is 1.1a. So XU limit divided by D is equal to 0.87, Fy AC divided by 0.36 FCK BD. So both side D is there, so cancel this and rearrange it. We need to calculate the AST. So AST is equal to 0.36 FCK B into XU limit divided by 0.87 Fy. After rearranging, so it comes. So our XU limit is equal to XU maximum. For that, XU limit divided by D is equal to 0.48. So I am moving D to here. XU limit is equal to 0.48 D. So substitute the D value. Simplify this. We'll get 216 mm as our XU limit value. So by using this formula, we will calculate the AST1. So AST1. So substitute all the value. Our XU limit value is which we have calculated just now, that is 216. So substitute all the value. Simplify this. We'll get our AST1 is equal to 1292.23 mm square as AST1. So call it as equation number 2. So